So section 2.4 talks about complex numbers. And what we're going to talk about here is using the imaginary unit I to write complex numbers, add, subtract, and multiply complex numbers, use complex conjugates to write the quotient of two complex numbers in standard form, and to find complex solutions of quadratic equations. So the imaginary unit I is when some quadratic equations have no real solutions. For instance, like x squared plus 1 has no real solutions. And again, if you were to graph that, you would have that parabola that doesn't cross the x-axis. But what happens is that if you were to actually solve it, you would find out that it has two real solutions. And so what happens is we have that this I equals the square root of -1. So that would mean then that I squared is -1. So every complex number can be written in standard form. So if we want standard form for complex numbers, that's your A plus BI form. So if you had this complex number right here, -9, the square root of -9 minus 5, you could separate that into the square root of -1 times the square root of 9 minus 5. Right, which the square root of 9 is 3, the square root of -1 is I, and then minus 5. So your A is always your real part, so this would be your A term, and then 3 is your B term. And so that standard form then would be that -5 plus 3I. So your formal definition of a complex number are that the A and B are real numbers in this A plus BI form. And A plus BI is a complex number. And so if B is 0, so if we had a 0 for B, then A is a real number. If B is not 0, then A plus BI is an imaginary number. So the imaginary unit I, we have the set of real numbers is a subset of the set of complex numbers. So it's true because every A can be written as a complex number if B is 0. So any real number you could write as complex just by putting plus 0I. So if you had two complex numbers, if you had A plus BI and then a C plus DI, if we wanted in standard form, they would be equal to each other if the A and the C were equal and if the B and the D were equal. So like if we said 2 plus BI needs to equal 2 plus 4I, if those needed to be equal, then we would know that B would have to be equal to 4. So if you want to add or subtract complex numbers, you add their like terms. So if we were adding A plus BI to C plus DI, we would add the A and the C, and then we would add the B and the D. Same thing with subtraction. So we also have that additive inverse, where if you have A plus BI and you add the opposite, A minus BI, you'll get 0. So if we practice adding and subtracting complex numbers, if we want, for part A, if we want to add them together, we're going to add the real parts. So 3 plus 2 is 5, and then -I plus 3I is positive 2I. If we go to part B, we have 1 minus 4. We might want to write this as 1 plus 2I, distribute the negative. So then we have -4 minus 2I when that negative is distributed. So we get -3 plus 0I. For the next one, let's distribute our negative. So we have 3 plus 2 minus 3I minus 5 plus I. So when you combine all the terms without I, 3 plus 2 minus 5, we get 0. And then -3I and I, we get minus 2I. And the next one, again, write it all out. So 3 plus 2I plus 4 minus I, distribute your negative, minus 7 minus I. When we combine terms, 3 and 4 is 7, minus 7 is 0. 2I minus I, we get plus 0I. So we would just get 0 for that one. So the properties that hold for real numbers are the associative property of addition and multiplication, commutative properties, and distributive properties. So if we wanted to perform the operations here, for part A, it says 5 times this complex number. So you can distribute that 5 through and get negative 10 plus 15i. For part B, it's like we're multiplying two binomials, so we're going to FOIL. So we'll do the first term, the outside term, the inside term, and the last term. So we get minus 3i squared. Now remember, I squared is negative 1. So this is really like saying 3 times negative 1, which is like plus 3. So we can combine this 8 and 3 and say 11 plus 2i. If we look at part C and we FOIL that out, we get 9 minus 6i plus 6i minus 4i squared, which again, remember, is negative 1. So this is really like saying plus 4. These two are 0, so 9 plus 4, we get 13, and we could say plus 0i. On part D, we're distributing a 4i, so we get negative 4i plus 20i squared. Remember, I squared is negative 1, so really we get negative 20 minus 4i. And the last one, when we square it, we can't distribute a square. We have to say 3 plus 2i times 3 plus 2i. So when we FOIL, we get 9 plus 6i plus 6i plus 4i squared, which remember is really like saying minus 4. So 9 minus 4, we get 5 plus 12i. So then if we look, it says, notice example 2c, the product of two complex conjugates is a real number. So when you have complex conjugates, if we look back here, if we have 3 plus 2i and 3 minus 2i, so if those b values are opposite and the a values are the same, they're called complex conjugates. So complex conjugates. And when you multiply complex conjugates together, what happens is those inside terms are 0, and so you just end up with whatever a squared and b squared is. You'll end up with a real number. So if we have to multiply by its complex conjugate, so if we have 1 plus I, that would mean we're multiplying by 1 minus I. If we were to FOIL it out, you get 1 minus I plus I minus I squared. Remember, those middle terms should always be 0. So minus I squared is really like saying minus a negative 1. So 1 plus 1 would give us 2. If we were to multiply 4 minus 3i, we would multiply by 4 plus 3i. So we would get 16. The middle terms, 12i minus 12i will be 0. And then we get minus 9i squared, which remember is like saying plus 9. So 16 plus 9, we would get 25. So sometimes we will be given problems where you're going to actually be dividing two complex numbers. And to write those in standard form, you have to get rid of the complex number in the denominator by multiplying by the conjugate of the denominator. So if we have to write 2 plus 3i over 4 minus 2i in standard form, we're going to take our 2 plus 3i and our 4 minus 2i, and we're going to multiply by the conjugate of the denominator, because we want the denominator to just be a real number. And remember, multiplying by the conjugate gives you a real number. So when we FOIL out the numerator, we get 8 plus 4i plus 12i plus 6i squared. And when we FOIL out the denominator, we get 16 plus 8i minus 8i minus 4i squared. So remember, this plus 6i squared is like saying minus 6. This minus 4i squared is like saying plus 4. So if we simplify that, we get 2 plus 16i over 20. And then to write it in standard form, we need a plus bi form. So 2 over 20 is your a. 16 over 20 is your b, and then you have the I, and then we could simplify it to be 1/10 plus 4/5 I. And then we also have the quadratic formula that we can use to help find solutions to quadratics that might not be real. So when we have that quadratic formula, if we get the negative under the square root, then we'll just write it. So if we get a negative under a square root, we'll just write it as the square root of the positive, and then we put the I next to it. So if we have to write the complex numbers in standard form, what you could do is here square root of 3. So we'll say the square root of 3 times I times the square root of 12 times I. So then we can multiply what's under the root. So we get the square root of 36 times I squared. So we get 6 times -1, which is really -6. If we look at part B, again, we have the square root of 48 times I minus the square root of 27 times I. So we need to get these to maybe somehow look like terms. So if we were to split this into a perfect square, we could say that this is the square root of 16 times the square root of 3 minus the square root of 9 times the square root of 3. So we would get 4 root 3 times I minus 3 root 3 times I. And so if you have 4 root 3 minus 3 root 3, you're just left with 1 root 3 times I. And then if we look at the next one, if we were to rewrite it as -1 plus root 3 times I squared, so that would be like -1 plus root 3 times I. If we were to FOIL it out, we would get 1 minus 3 root I minus, definitely did not write that. That was supposed to be minus root 3 I minus root 3 I plus 3 I squared, which is really like a minus 3. So if you have 1 minus 3, you have minus 2, and a minus root 3 and a minus root 3 is a minus 2 root 3. And then we still have that I with it. And then we also have quadratic equations. So if we were going to use complex solutions of quadratics. So here, if we just have an x squared plus 4 equals 0, let's say then the x squared equals -4. So x would equal the plus or minus square root of -4. The square root of -4 is 2i. So if you don't have that middle x term in there, just move the number over, take the square root, and make sure you remember plus or minus. For part B, we actually have to use quad form. So x equals the opposite of b plus or minus the square root of b squared minus 4ac all over 2a. So now if we simplify, we get 2 plus or minus the square root of -56 over 6. So if we were to think about some perfect squares, we could say 2 plus or minus 4 and 14 is 56. So we could say the square root of 4 times the square root of 14 and then times I to get rid of that negative underneath over 6. So we would get x equals 2 plus or minus the square root of 4 is 2. So 2 root 14i over 6. And then if you notice, the 2, and the 6 all have a GCF of 2. So if we divided everything by 2, we would get 1 plus or minus the square root of 14i over 3. You don't divide the 14 because this whole thing is one term. And so dividing that 2 takes care of all of it.